Today we are going to do section 4.8 on page 459 of the Lagrange multipliers. But before we start, I want to remind you some of the vector stuff that we had a couple hundred years ago that might be easy to forget. So a quick refreshing of what that was. A vector value function is something, look at my red dot location, okay? Something that's RT equals to FTI plus GTJ, right? Where f and t, where it describes a curve in space. As t increases, then this thing moves around in space. So that's the vector function. Now the vector function can also be written with the bracket thing. See the bracket? Whether it's in 2 or 3 dimensions. At least I call that a bracket. I don't know what you would want to call it, but that's another way of writing it. So next, the next theorem is the differentiation. Now, if r of t is equal to that thing, then r prime is just the components. You take the derivative of it. That's all. Okay, and so that's that. Next, I want to remind you that what is the unit tangent vector? The unit tangent vector is the derivative of r, okay, r prime of t divided by its own magnitude. Focus on the red dot area. So, and that makes, therefore, the unit tangent vector is tangent to the curve of r and also has the length of 1. And so that's the unit tangent vector. Next, the arc length function. Now, if S is represent the length of this arc that we're talking about, and the length is given by, look at the red dot. We don't care what the length is given by. What matters is that ds by dt happens to be equal to the magnitude of r prime of t. All right, and then if you want to see the arc length, what happens is then you can represent instead of r instead of t in terms of t, you can express r in terms of s. Okay, so and that is called the arc length. See right down here, arc length parameterization, okay? And that's at example 3.10 if you want to look at it. And specifically, we're going to prove that r prime, the arc length, when you parameterize that way, that is r is in terms of s instead of t, then r prime of s is always equal to 1. It is the unit tangent vector, which I'll show you in a second. But in the meantime, let's move on here. The next thing I want to show you is, so the point is ds by dt is equal to the magnitude of r prime, okay, which I have also written right here. And we need that in a little bit. So, and the last thing I need to remember is, I want you to remember, it's not the vector, it's just something we did maybe 30 pages ago, that the gradient is normal to the curve. Okay, that's a theorem that we recently had, but I just want to refresh your memory on that. The gradient, that's the del f, grad f, is always normal to the what curve is that? To the level curve, sorry. I should specify, in other words, the contour lines, okay, and we proved that a bit earlier. So having said that, so that's good. And next, I want to look at this for a second. Now, the proof that Lagrange theorem involves a statement that says that r prime of s is the unit tangent vector, okay? Which is okay, except that I don't remember us ever learning that or deriving it. So I decided to just derive it here to show you how it came about. It's pretty straightforward. And so that when you read it in the proof, you're not like, where did they get that, right? So to prove this, r prime of s being the arc length parameter, it happens to be equal to the unit tangent vector. So we start with this, okay? ds by dt is the magnitude of r prime of t. We saw that a little earlier, okay? And then t of t is definition. And then so r prime of s, by the definition of the derivative of the vector, is dx by ds plus dy by ds, which we also seen earlier. So our prime of t, in other words, these are different. I'm taking derivative of with respect to different parameters, okay? But the principle is the same, right? If it's with respect to t, then we just put t down here. That's all. And then I'm going to apply the chain rule, okay? The chain rule states if you have dx by dt, that's the same as dx by ds and then ds by dt. If s, you can express s in terms of t, which you can't. But anyway, that's how the chain rule works, and the same as on this side with y. Now, once you write that down, then you realize something is that what is dx by ds? Let's plug this, factor this out. ds by dt, I'll factor it out as this. Okay, our prime of t. So I'll write it down here. And the rest is just dx by ds, which is our prime of s. So I wrote it down here. And then that's our prime of t, right? So then I do the division, then our prime of t over our prime of t is magnitude, which is by definition the tangent of t is you divide it over here, so you have left our prime of s on the other side. That proves that our prime of s is identical to the tangent vector. Okay, so therefore it has a unit of 1. Now we know that our prime of s is the tangent, because it doesn't matter if you talk about t as what's the diff, okay, the derivative is the tangent. Now the question is what is its magnitude? So in this show it's that if you calculate if you do the parameter s, arc length parameterization, then our prime happens to be always be the unit tangent vector already. Yeah, so that's all I want to talk about that, and we'll use that in a second for proof of the Lagrange multiplier. Now the next, let's consider what that Lagrange multiplier is. First, let's consider a curve in this is a curve, okay, and a contour curve of the function gxy, and being that is 0, is on the ground. So we have a curve on the ground, and let's draw it something like this. Okay, here is g-axis, and g might be some curve on the ground. Okay, because it equals to 0. Now the gradient of g, of course, as we mentioned earlier, the gradient is going to be g. I should first mention that this isn't just a curve, but this is the contour curve of gxy. Okay, it's the contour curve when the level is at 0. So then the gradient of f then is going to be perpendicular to this contour curve at any given point. So here's the gradient. Okay, so del g, I mean, did I say gradient of f? I mean the gradient of g is going to be perpendicular at each point because this is a level curve. Okay, the level is at 0. All right, and next we are going to, this is by the way, this is just the xy plane. That is, we're looking down at this thing from space, okay? This is like a map, okay? And in the meantime, we'll draw some contour curves of the z. The z function is in space, they're not just on the ground, but we'll draw its contour functions. It might look something like this, right? It might go like this, and then go like this. This is a mountain peak, and the contour curves keeps going, you know, and so on and so forth. And as the landscape of the f, we're looking down from space here, okay? So this is a map, and we can see all the contour lines. Now similarly, the del f is going to be perpendicular to its contour lines, just like del g does. Now, as you can see, there is a point where you can draw a contour line, okay, close enough to this curve so that you will barely touch it, and that is okay. Let's say this contour line, right, is that at that point, as you cross this point, this line g of x along the f, then it will reach its highest point where it touches. Okay, because as you move along, right now I'm moving on the surface of f, but where the shadow, my shadow is on on the G line, okay, on this line, but I'm not on the shadow, I'm not on the ground. Right now I'm walking along on top, okay? As I walk on top, as you can see, the contour line of F, as you draw more contour line close to it, eventually it reaches a point where one of the contour lines, if you just draw one that's close enough, will be tangent to the G if everything's differentiable and smooth and there's no weirdness going on. Okay, so if that's the case, then at this point, then first you can see that if you walk along there, okay, along here, then you will reach the highest point and then go back down again, because this is a contour line, right? This line is taller, is at a level higher than this one. So you go from here, go to the highest point, and then go down again. So therefore, on this line, the function f is maximized at this point where the contour line is touches the curve. So therefore, at this point, then del f, okay, so del f, say maybe go like this, right? This is del f. And so at this point, del f and del g are parallel because they're both perpendicular to this to the curve gxy equal to 0. Okay, and remember both dels, the gradient, are on the ground. They only have x and y values. Okay, they themselves don't have z values, right? So they're both perpendicular to this curve, being that the del f is perpendicular to your contour line, and the contour line is tangent to the curve. So therefore, del f is equal to some constant lambda times del g. Now that means that that just means that they are parallel. The reason they're parallel is because they're perpendicular to the same thing, so they have to be parallel. And when vectors are parallel, then one equals to the other one multiplied by some fixed constant, and we'll call that constant lambda. And that is the whole point of the Lagrange multipliers, okay? And the unofficial proof. So having said that, we're going to actually prove the Lagrange multipliers. And that's as shown in the book. Now, let's see. So let's look at theorem 4.220, where the Lagrange multipliers. If f and g are functions of two variables each, they have continuous partial derivatives on some open set, and then that contains some smooth curve g of xy, all right? And then f, where along the function f along where g of xy equal to 0, okay, that along that curve, that is the value of f, which is on top, but gxy equal to 0 is just the ground curve, okay? But the value of f along that curve is kind of like a border, right? The value of f along that curve is, if it has a local extremum, that is a local max or local min, then, and that the gradient is not 0, let's not worry about it being 0 for now. Okay, and being 0 is not interesting. And then there's a number lambda called a Lagrange multiplier such that this relationship holds. Okay, that del f equals to lambda del g. In other words, they are parallel, the two vectors are. Because del f is a vector, right? Remember that, and so is del g. And the two vectors will be parallel. Now the proof of that is, let's keep looking. First, we will say gxy equal to 0. That's what we're given. That's a curve, and we're going to represent that curve with some kind with a parameterization. That is, we'll plug in some s, okay, in such a way that x equal to x of s and y equal to y of s, and when you do that, you plug it into the g and it'll fit. Okay, so, but the s, however, isn't just any old s. It's the arc length parameterization. Now, why do we do arc length? I'm not sure. It's nicer, I guess. And if we're you can use any parameterization, so why not use the arc length? And so that's why. So it's specifically mentioned that s is the arc length parameter. All right, let's moving on. So then now that we have it parameterized, let's plug everything into f. Okay, f is right here. We plug x1 in f. Now z, which is f of xy, is going to be equal to something in terms of s, because x and y both become something of s. So then, and then we also know that along this path, if this is true, the maximum or minimum point is going to have the derivative of 0, right? And this is from one-dimensional calculus derivatives. And so anyway, the derivative is going to be 0. So we'll write down that as 0, and we'll take the part. What is dz by ds? dz by ds by the chain rule is equal to partial f partial x dx by ds, right? And plus the y part, partial f partial y dy by ds. Now, and this is this is fine. And the next line, your book has it way off. Okay, it should read something like this. I mean, it's obvious it should. And so please note that in your book. So to rewrite the sentence, that's the same as the vector del f, f of xi plus f of yj, okay, dot product of the other part. What is that? It's dx dsi and dy dsj. No, all right, so that is what that means. Now at this point, I want to show you what we did before, is this thing right here, dx dsi and dy dsj, which is r prime of s, okay, which is exactly the unit tangent vector. And by the way, we're evaluating all the stuff at the point that we're interested in, the maximum point. The maximum point is where s equal to 0, okay? Because we're parameterizing with s. When s is, we start counting at s is 0 as the initial point. So when t is 0, then we have, so this whole derivative is evaluated at s equal to 0. Now, if in that case, you can see that at that point, then the del f, the gradient, dot the tangent is going to be equal to 0. See, and if that's the case, then the gradient f is going to be perpendicular to the tangent of the curve. Now, and then the next thing we notice is the gradient of g is always tangent to its own curve, right? So gradient g dot the t0 is also equal to 0. Now, if being the gradient f and gradient g are both on the ground, they are two-dimensional vectors. If they're both perpendicular to something on the tangent, then they have to be parallel. Okay, there's no other way because they can't get out of the ground level. They are always on the ground level. Okay, and because they only have I and j as their vectors. So then if they're both perpendicular to the tangent, they have to be both normal to the tangent. Normal means perpendicular, and therefore they must be parallel. And if two vectors are parallel, then one is the multiplying of another, okay, some constant. And so then that's how you come up with, and that would that marks the end of the proof of the Lagrange multiplier. Now when I say one is the other equals the other multiplied by something, the lambda can go on either side. For example, you can write it like this if it's more convenient, depending on your problem, equal to del g. Okay, that's the same thing, because all I said is one multiplied by something equal to the other. It doesn't matter what you're multiplying. You can multiply by 2, move it over is 1/2. What's the difference, right? And of course, lambda, it can also be negative. No, nothing wrong with that. The point is they're parallel, although they might point to the opposite direction. So let's look at the next page. This is we're now on page 460, where there's a problem-solving strategy to summarize how to actually use this. Now remember, when you say this, what that means, you have two vectors here, okay? When two vectors are the same, that means their x components are the same and their y components are the same, which gives you two equations. And then together with this original thing that was given to us, now we have three equations. 3 equations and 3 unknowns. Guess what you're going to be doing, okay? It's called solving simultaneous equations with 3 equations and 3 unknowns, which is something you did in algebra. If you don't remember how to do that exactly, the book gives a very clear explanation to remind you of how to pull this off. And so please do example 4.42 as part of your homework. Next, let's look at example 4.43. Same thing. You have some problem of maximization. You set the gradient of f equal to lambda gradient of g, which means you have two equations out of that for both the x component and the y component. And then you have original g equation. That's a third equation. So now you have three equations with three unknowns. And you're going to solve for x, y, and lambda, and then plug stuff in to tell them what they want. Okay, maybe they want what is the maximum, what is the minimum, what's x, what's y. But nobody's going to ask you what's lambda, okay? Because lambda is just a means to an end. So we don't care about lambda in itself. Once we're done with it, we'll ignore it. Okay, so let's next move to page 464, where we have more variables. Instead of just x, y, now we have x, y, z. Now what? Well, if you have x, y, z, you have three variables there, plus lambda is four variables. But being that you have x, y, z, the gradient also has three components, right? X, y, z. So you have a total of four variables and four unknowns. And you can do that the same way as three variables and three unknowns, except it's going to take you a whole lot longer. But please do it anyway and give yourself enough time. I don't know. Pretend this is a big long challenge that it's important to go through this, okay? That way you get a feel for it and the proof that you can. All right. So even if it's very tedious, there's a time to keep hitting it until you pound the tedious problem to death. So please do example 4.4 as part of your homework. And moving on, and the next page, that is for example 4.45. That's even worse. Now we have two constraints. And how do you handle two constraints? Here is how you handle it. Right above on the same page of example 4.45, you see how to handle it. Now you have two lambdas. And we're not going to prove that, okay, or even figure out what that means, because you're talking about gradients in 3 dimensions, which means your object is in 4 dimensions, which we can't visualize, so we're just going to ignore it. But that doesn't mean you can't calculate it, though. You can still do the math like you always do. So the math says we are going to do this, okay? You have lambda 1 and lambda 2 with two other gradients for the constraint equations. So that gives you 3 equations. Then you still have the 2 constraints, right? G and H equal to 0. That gives you 2 equations. That's a total of 5 equations, all right? Which is and 5 variables. And you're going to plug stuff out, and that is going to be, well, I think they're just going to keep it simple for you, or something. Anyway, so please do example, even then it's going to be a pain, right? So please do example, what is that? 4.45 as part of your homework. And have some patience and persistence and tenacity, okay? And all those virtues, gather all up and build, and you'll build a ton of character by doing this type of thing. And that marks the end of this section. Now homework for section 4.8, which is on page 469. Please do problems 359, 363, 367, 371, 375, and 379. The homework problems aren't near as hard or complicated. None of it is really hard, but they're all extremely long and tedious. But the homework problems aren't near as bad, actually. So please do the homework, and when you're done, I want to talk about one of them that I happen to do for no reason, actually. Now that you're done, please let's talk about problem 371 real quick. I just decided to do that problem, no reason, and it doesn't turn out to be very bad. See, what happens is, of course, we have a function we need to maximize, right? And there's the surface of the graph that we're maximizing. So we follow the rules. The rule says you need to take del f and del g, and then you have your graph, and then you line everything up with lambda. That is del f equal to lambda del g. Now, after I did that, I decided that's not working out nicely, so I moved lambda to the other side. Doesn't matter where you put it, okay? And then things came out better. At least I don't have to, lambda doesn't have to be in the denominator, which is annoying to me, okay? So then you calculate that. You line stuff up and figure out the x equal to 2x equal to 2 lambda, etc. And figure out what x is, plug it into the g equation, And then you calculate, I came up with lambda squared equals to 2. So lambda is plus or minus 2, which plug it into the x, y, z based on these formulas. Then we come up with a bunch of numbers. And now remember, lambda is either plus or minus, okay? When it's minus, it will be the negative value and the minimum value. When it's plus, it's the maximum value. Okay, so I think in the problem, we are only required to do the maximum value. So we plug the positive option in, and that came out to be 19 and 19 square root of 2, which I checked is the right answer at the back of the book. And with that, that comes the end of our section.